Welcome to lecture 24 in our class on stochastic processes, where we want to conclude our discussion of the Black-Scholes model. We want to show that every square integrable option is attainable, which is sometimes also called the completeness of this model, which means that every reasonable option can effectively be attained by a replicating portfolio strategy. We want to show that this gives a general pricing formula by means of a properly defined expected value. And we want to apply this concept to also the case of exotic options, at least in one example, when we will discuss in the end a so-called up and out European call. So let us recall for this the basics of the Black-Scholes model. The Black-Scholes model is a model containing two assets in which an investor can invest. One asset is given through a solution of the of the Black-Scholes stochastic differential equation with parameters alpha and sigma. Alpha is the drift parameter, sigma the volatility, and the process starts at an initial stock position S0. That's the stock dynamics for a stochastic process that models the actual asset which has a random behavior, and then we have a second asset which behaves in a non-random fashion, which is just performing a continuous interest rate dynamics, and the interest rate here is the parameter R, and we want to assume that this bank account, if you like, value is starting from the initial value 1. These are the two assets in which we can invest. And an option, or it's sometimes called a derivative, or it's also called a contingent claim, all these are the different names for the same thing, is just a path functional which converts the behavior of that stock as it is observed on the whole interval, time interval from 0 to t, into a certain payoff, and that is described through a certain path functional phi. And the fundamental question is, what is a reasonable price for such a privilege or for such a pledge if you own it, or if you sell it, or if you buy it from someone on the financial market? So in abstract terms, this is a certain bet that produces a certain payoff depending on the behavior. So that would be the payoff of this bet, and of course you would have to pay a certain price at the beginning of this game if you want to play this bet. And the question is, what would be the fair price? There is an agent who sells this bet in the sense that he collects some money at the beginning and then pledges to pay this amount depending on what the future outcome or what the future behavior of the asset will be. And there's a potential buyer of the bet who pays a certain initial amount and then receives this promise phi as a promise for a future payoff. And so that's a claim that this buyer owns after he purchases this, and the claim, the actual total amount of the claim that he will make at the end of the time period will be contingent on what was observed in the time before, and therefore it's sometimes called a contingent claim. There is the idea that instead of investing in such a contingent claim, you could also invest in a self-financing or in portfolio strategy, which is given as a tuple of two stochastic processes, eta and beta, which at each moment of time represent the amount of number of units we own in stock, and the a number of units we own in this fixed income asset B. And therefore the total value of that portfolio strategy at time t is the value of the shares of the stock that we own at that time, which is the total number of shares times the value of the share at that moment. And additionally to that, we have a value of the fixed income asset, of which we own at that moment of time beta t times many pieces. So that's our total wealth if that's our portfolio at time t. And we call this portfolio strategy self-financing if the changes in value of that portfolio are caused exactly by the changes of value in the stock and in the fixed income derivative and fixed income asset, and by nothing else. And this is represented by this expression that the infinitesimal increment is exactly this linear combination of infinitesimal increments of the stock and the bond or the fixed income, where the proportionalities here in this linear combination or this coefficients are exactly the total amounts of units we own in the respective asset. We call a contingent claim or an option attainable if we find a self-financing strategy of a portfolio which is so that at terminal time this strategy matches exactly the payoff which is promised under the option phi. That is the basic setup of our Black-Scholes financial market model. And for the complete mathematical analysis which is to follow, we shall introduce the so-called discounted processes, namely the discounted stock and the discounted portfolio value process, which is obtained from the stock process or the portfolio process simply by relating that to the value of the fixed income derivative, which is nothing but by multiplying with the factor e to the minus rt both. That's a simple transformation which will turn out to be very useful, and economically it corresponds to the fact that a stock value at moment of time t can also be priced at time zero. So since that stock value at time t, which is in the future from time zero, then will be realized probably at a later moment of time, as seen from time zero, we have to depreciate, if you like, that fact, accounting for the delay in time. So this is what is called a discounting future value from a perspective of today. Okay, but mathematically these are just certain transformations. And we have a first lemma on these two processes, namely, first of all, we can write down now the corresponding stochastic differential equation that this discounted stock process satisfies. And we see that the discounted stock process also satisfies a Black-Scholes type stochastic differential equation, but now with a modified drift, which is diminished by exactly this factor r, which is the interest rate which appears in this discounting, and else nothing in the differential equation is changing. The second statement that will be extremely useful further on is the fact that if a portfolio strategy or a portfolio strategy in pi is self-financing, if and only if the discounted portfolio value process can be written as eta times the increment of the discounted stock value process. Probably I should indicate here, and I could have done that earlier, that as usual, whenever I am writing an equality of such differentials, this is to be understood as an equality for the corresponding family of stochastic integrals. Okay, so let me say it again. The portfolio pi is self-financing if and only if we have this simple representation of the changes in value of the discounted portfolio value by means of the stochastic processes of the portfolio strategy in the stock dimension integrated against the change of value of the discounted stock price. Claim 1 of this lemma is a simple exercise which I leave to you, and let's therefore just focus on the second statement, namely first we write down what the value of the discounted value of the portfolio is. Well, it's eta times the discounted value of the stock times beta plus beta times the discounted value of the bond. but the discounted value of the bond by construction then is just a plain 1. Moreover, of course, the discounted portfolio value is this product of e to the minus RT times the V. So therefore, by product rule for the stochastic differential, I can expand this product of two processes by the Leibniz type product rule, which is therefore the first process times the increment of the second, plus the second process times the increment of the first, where the first increment is infinitesimal increment of e to the minus RT, can be written as e to the minus R times e to the minus RT dt. That's just the chain rule. And note that in this case, the product or the Leibniz rule has no e2 correction, because this first factor process is a process with differentiable and in particular paths of vanishing second order variation of quadratic variation. So therefore we have no e2 correction term. Okay, and in this representation I can now expand the differential of the V according to the requirement that pi be self-financing, so that's this part. And also I can expand the V according to what it actually is, namely it's just this linear combination of the B and S values with the factors eta t and b. And now I see, if I take a closer look, that I have a cancellation here of this term with, before I do that, before I see the cancellation, I have furthermore to expand the dbt, which was by assumption an r times bt times dt, and now I see a cancellation of bt times r dt with an e minus r factor with exactly the same term which is in the second summoned, but with the prefactor minus r. So there's a cancellation, and I'm left with these two terms for the increment of the discounted discounted portfolio value. And therefore here I can pull out this eta factor, which is appearing in both of these summons, and I see that I have in the end an e to the minus rt dst, and I have an st times minus rt e to the minus rt dt, which altogether is just by chain rule or by product rule again, the differential of e to the minus rt st, which is just the ds tilde. So this tells me that if I do have a self-financing strategy, then in fact the infinitesimal Ito increment of the stock value, discounted portfolio value, is really written like that. And of course this is a chain of equalities, and I could also use this chain of equalities or read it in the other way around, which would then tell me that the increment of the dv must be of that type. Okay. And as a corollary of that, I find a useful statement which tells me that if pi is replicating and of course self-financing, then the discounted payoff of this contingent claim can be written as the initial value of that replicating portfolio strategy plus the integral of the stock component of the portfolio strategy integrated against the increments of the discounted stock process. Well, why is that true? Well, the discounted payoff of the option is by assumption the discounted terminal value of the portfolio, which is the portfolio value twiddle at the terminal time, but I have just seen that the terminal value, that the portfolio value, I know how the increment of that portfolio, of that discounted portfolio value process looks like, so therefore I can write that also as V naught times the integral over the increment, which is just this. And here note that V naught tilde is the same as V naught. So at time equals 0, there is no distinction between discounting, the discounted and the non-discounted process. And that's a corollary to the previous computation, that we have this representation. The next lemma, which at this moment looks not necessarily quite related, but will turn out to be extremely useful, is the following, and it will make use of the Gazanov theorem. Namely, if I convert the probability measure, which is the underlying probability measure on the probability space which carries the Brownian motion with respect to which the Black-Scholes model is defined, then I can introduce a new probability measure on that measurable space in the now familiar form by defining a new one, Q, a new measure Q, which is then defined on the sigma field at terminal time t. Namely, for a set E in that sigma field, I define Q of E to be the integral of a certain Radon-Nikodym derivative, or Radon-Nikodym density, over the set E with respect to the old probability measure P, where the Radon-Nikodym density that I choose here is the exponential martingale, which is obtained from the scaled Brownian motion, where the scaling factor is a minus alpha minus r over sigma. If I do so, then I can consider a perturbation of my Brownian trajectories by means of a constant drift process, which has alpha minus r over sigma as drift. This would be a process which has, in comparison to WT, changed trajectories because I have added this drift component. But if I sample now these trajectories using the probability measure Q, then under this new probability measure, Q, the process W tilde, is again a standard Brownian motion. So I introduce a new synthetic a new synthetic measure on my probability space, which allows me to interpret these tilted trajectories of which change the old Brownian trajectories into Brownian trajectories with a tilting. If I generate now these trajectories with a different statistics, then the corresponding observed process will be again a Brownian motion. That is obviously, or already here, we think that this is somehow related to the Gazanov theorem, and it is in fact the case. So we are talking about an application of the Gazanov theorem in the case when we deal with exactly this exponential martingale or Dolian-Dart exponential. And in order to apply the Gazanov theorem, we would need to convince ourselves that the Dolian-Dart exponential is really not only a local but a true martingale. For that, we have to check our Novikov type condition or Novikov kind condition for a certain parameter p bigger than 1. We want to make sure that the corresponding bracket process of that transformation of that martingale, which is used for the Dolian-Dart exponential, that this bracket process is exponentially integrable. But for that particular case here, the bracket process of omega is obviously just the identity function. We have to evaluate that at terminal time t. So the question is whether this random variable is finite, has a finite integral. But it is not a random variable after all, because the quadratic variation of omega is deterministic. It's a Brownian motion. And so it's just this quantity. And that's, of course, a finite number. So therefore, the Novikov condition is fulfilled, or the Novikov type condition is fulfilled. And we realize that this tilted, or this tilde process, can be written as the old trajectory minus the bracket of the old process with that martingale that is used inside the Dolian-Dart exponential. So therefore, from Gazanov theorem, we know that this omega tilde is a Brownian motion when we generate trajectories with the probability measure Q. And if we work with this new probability measure Q, which is at this moment a mathematical artifact, if you like. Then we can draw a couple of conclusions, namely, first, this S tilde process, so the discounted stock value under Q, is a martingale. And moreover, if we ask for the ask and the bid price for the contingent claim phi, then we have a relation between the two, which is intuitively clear, but not yet proven, namely that the ask price of that contingent claim is above the bid price of that contingent claim, and that they are both bounded from below and from above, respectively, by the expectation of that contingent claim by the expectation of the discounted contingent claim under the probability measure Q, under this synthetic measure Q. So it says that the seller of the option would not sell the option at a price which lies below that expected value of the discounted payoff of that option under this probability measure Q. And likewise, the buyer of the option would not buy that contingent claim at a price which is above the mean payoff of that option if we discount the payoff and if we take the mean value with respect to that particular probability measure. And moreover, if the claim or the contingent claim is attainable, so if we find at least one self-financing portfolio which attains perfectly the value of phi at terminal time, then we have equality in those two inequalities above, which in particular means that there is a price on which the buyer and the seller will agree, and this price will be exactly that number, namely the mean payoff of the mean discounted payoff under that probability measure Q. Let's prove these two statements. First, we write again the stochastic differential equation for the discounted stock dynamics. And this stochastic differential equation can be rearranged by pulling out sigma times S tilde in front of the two brackets here. And we see that what remains inside the bracket is the dw plus an alpha minus r over sigma times dt, which is sigma times S tilde times dwt, where dwt or wt is exactly this process which was appearing in the previous lemma. And we know that under Q, if we generate trajectories of W2, of W tilde according to the Q mechanism, which means that we sample from the Brownian motion trajectories, but not with the initial probability measure. We choose not sample not with the initial probability measure, but with the Q measure. Then this dW process is just a martingale, and so therefore we find that the S tilde process can be written as the stochastic integral of some process with respect to another process which under the measure Q appears to be a martingale. So therefore the S tilde process is a local martingale, and it's easy to show that it's uniformly integrable. So that's in fact a true, honest martingale under Q. That's the first claim. The second claim regarding the relation of the ask and bid prices in comparison to this expectation, let pi be a self-financing strategy which at terminal time produces a portfolio with a value no less than phi. Then, of course, also the discounted phi is less than the discounted portfolio value at that terminal time, but we know that the discounted portfolio value by self-financing property of eta and beta of this portfolio strategy can be written like this. Now that's an inequality which is correct almost surely for almost all P, And Q and P are equivalent, which means to say that they have the same zero sets, which is a little exercise to show, but not so complicated. So since they have the same zero sets, the same inequality is also true. Q almost surely, and in particular, if we hit this inequality with the expected value, we find that the expected value of the left-hand side is less bigger than the expected value on the right-hand side, in particular if we take expected value with respect to the Q measure. But on the right-hand side, we have the expected value of two quantities, the second of which is a stochastic integral with respect to a Q martingales starting at 0, so therefore it's a 0, and only the first summand in this expected value contributes, but the first value, or the first summand in this expected value, is a deterministic number. It's just the portfolio value at initial time, which is deterministic, and therefore we have this V naught of pi on the right-hand side. So we have that EQ, this discounted expectation of the contingent claim under the measure Q is bounded from above by any initial portfolio value for any self-financing strategy whose payoff is above the phi option. And so therefore this expected value is still less or equal than the infimum of all those possible initial portfolio values, which by definition was exactly our ask price. So the minimal price under which a seller would rationally sell the option. The argument for the corresponding lower bound is similar, just likewise, and so we find that this inequality is proved. Finally, if the option is attainable, which means that there is at least one strategy which matches that payoff exactly, then we have one joint element in these two sets of options of portfolios which lie below and above, which in particular means that the infimum of the one must be the supremum of the other, since they are already aligned, so they can be compared, but they have a joint, these two sets over which I take the supremum or the infimum have one common element, so they have the same infimum or supremum respectively. And in particular, I have this equality, which means that in the attainable case, there is agreement between the seller and the buyer on the minimally acceptable selling and the maximally acceptable buying price of that option, and that's exactly this expected value of the discounted payoff under Q. As a corollary of this consideration, we also note that if phi is attainable in the Black-Scholes model, then the portfolio strategy with regards to the risky asset is uniquely determined by the fact that the discounted payoff of that option can be written as this stochastic integral with the eta against the discounted stock process, and the price of this option then is just a rephrasing of what we just have said, is then given by the discounted expected value of that path functional, where we evaluate the path functional now on a geometric Brownian motion, which has parameters sigma and r, and which starts in the initial position S naught. Okay, so we have, if you like, before in this statement before, we just had this abstract Q, which was not, which we could construct, but it looked a little abstract. And here we have a slightly more concrete representation how to compute this this expected value, because we can identify the statistics of this process S, of the old process S, under the new measure Q in an explicit fashion, and we know that will be argued below. We can see that this S process under Q must be a geometric Brownian motion with these given parameters. Okay. Again, this is a lemma which contains two statements. Let's start with the uniqueness of the eta component of the replicating portfolio strategy. Namely, assume we have two possible replicating strategies for the same option phi. Then this is two ways to represent the same random variable. So in particular, if we take the difference of the two representations, we get a representation of the zero random variable, where this zero random variable is the sum of a certain number plus a stochastic integral against a martingale. So therefore, if we hit this equality with the expectation operation, then the stochastic integral has zero expectation anyway under Q. I should probably write properly that this is the expectation with respect to the Q measure. So if we do so, then we find that since the stochastic integral vanishes in the expectation, that this C0 minus C0 prime, which must be zero, because it's just the difference of the constants there, which has zero expectation, so therefore the constants, the difference is zero. And finally, therefore this stochastic integral is the zero stochastic integral, and that can only be the case if the integrand is the zero integrand, because if I take this stochastic integral squared and take the expectation of this, by Ito isometry with regards to the stochastic integral against the S tilde martingale, I can also write this as the integrand squared integrated against the bracket process of the S tilde process of the martingale, which is a strictly positive bracket, and so therefore this can be zero only if and only if this integrand is the zero process. This is the uniqueness of the eta, and it's easy to show that if the eta is uniquely determined by self-financing requirement, therefore the beta process is also uniquely determined. And as far as this explicit representation of the statistics of the S process under the Q measure is concerned, we write down the initial stochastic differential equation for the S process, which we rearrange a little bit by inserting and subtracting alpha minus r times S dt, which then by multiplying this or factoring this out in front of the S, the whole thing can be written as a sigma times S dw plus alpha minus r over sigma dt, where we recognize that the dw tilde is appearing here as the right-hand side, and dw tilde under Q is a plane Brownian motion. So therefore, if we generate trajectories, if we generate W trajectories under the law Q, which means that if we look at solutions of this process under the law Q, we see that under the law Q, the solutions of this S process can be written as solutions to this Black-Scholes differential equation, whose solution we know precisely because this is then just a geometric Brownian motion with parameters r and sigma and nothing else. So therefore the law of this process under Q is the same as the law of the geometric Brownian motion with these parameters. And so therefore, if I'm asking what's the expectation of this phi functional under the probability measure Q, then it's just as good as if I use this phi functional and apply it to a process with the right statistics and compute the expectation of that. And this is what is expressed in this statement here. So that gives me a way to basically compute pretty precisely the expected value on the right-hand side under this synthetic measure, because all I need to know about this synthetic measure is how the trajectories of the S process look under the new synthetic measure Q. Finally, we want to show that the Black-Scholes model is complete in the following sense. every option, every path functional, which is square integrable, is attainable. This means that under this rather modest integrability condition, every hypothetically terribly complicated option can be replicated by a properly chosen and then unique portfolio strategy. Okay, in order to show this, we will use the Martingale representation theorem that we have proved in the last segment, in the last session. Recall that under the measure Q, the discounted stock process can be written as sigma S tilde dW tilde, where W tilde under Q is a standard Brownian motion. So, as we had already seen, this means that the S tilde process under Q is this geometric Brownian motion. In this case, since it is the discounted version, the R parameter even vanishes, and therefore it's the geometric Brownian motion with drift parameter 0. And likewise, as we had just said, the parameter or the process S alone, which is the not discounted version, will then be this geometric Brownian motion. So that's just a repetition of what we had just discussed one proposition before. What we also see is that any functional of S, which is our option, is in fact a functional of the corresponding driving Brownian motion or Brownian driving process omega tilde. Because through this transformation, which relates the W tilde to the S process, we see that the S process is actually just a result of a certain mapping of W tilde. So hence, this phi functional is in effect a functional which we then might call psi of the corresponding driving process omega tilde, which is a Brownian motion under Q. So omega tilde is a Q martingale, and not even a Q martingale, but even a Brownian motion. So basically we have a Martingale representation theorem for any functional which is a functional of W tilde. In particular, if phi is a bounded functional, then under Q, this psi of W tilde, which is just a rewriting of the phi of S, that's then just is the same as the expectation of the phi functional in terms of S. That is then a finite number, and I should probably use the second moment here in order to relate to the condition of our Martingale representation theorem. So in particular under Q, also since phi is bounded, the second moment is finite. And hence we can apply the Martingale representation theorem that we have proved in the previous section to this psi functional as a functional of psi, which is also a phi functional. Or if we want, we can also apply that to the discounted version, which is just the undiscounted functional multiplied with a certain deterministic factor. So also the psi tilde functional of that omega tilde process allows for an interpretation in terms of an expected value and a certain stochastic integral. That's an equality which, to start with, is correct for Q almost every realization of the W tilde process. But as a simple exercise will show, the two measures P and Q, which are related through the Gazanov transform by means of an honest martingale, a non-negative exponential martingale, they are equivalent, which means that they have the same zero measure sets, and therefore this equality is correct also P almost surely. Now that is not yet the representation that we want, because attainability for us was equivalent to saying that this random variable, which is the contingent claim, can be represented as a certain constant plus a stochastic integral with respect to the S tilde process. So we want to represent this integral as an integral with respect to the S tilde process. For that matter, we recall again that the stochastic differential equation for S tilde is of this simple type if it involves only the W tilde process, which I can rearrange if you want by a simple application of Ito formula. I can convince myself that this is true. I can also write the dW as 1 over sigma times 1 over S tilde ds tilde, at least as long as this inversion is admissible, in the sense that at least as long the S process is still positive, which is the same as asking that the S tilde or S process is positive. And in order to convince ourselves that it is sufficient to make this replacement on this time interval before the S process hits the level 0 the first time, recall that S tilde under Q is a martingale, and also it's a non-negative martingale. And it's a well-known property of non-negative martingales that whenever they hit 0 for the first time, they remain 0. That's again a simple exercise, which I might put on the exercise sheet. So if we have a non-negative martingale, so that's a process in which, when you look forward in time and compute the conditional expectation given the current state or the current information, then the future level, or the expected value of that, is the current level of the process. Well, if the process is 0 at any further time, the expected value of that non-negative random variable must be 0, and the non-negative random variable has expected value 0 if and only if it is 0. So therefore, it is easy to see that a non-negative martingale will remain 0 once it has touched the level 0 for the first time. So therefore, this S tilde process is just as good, or even the S process in terms of non-negativity or strict positivity, it's the same. So therefore, the S process is just as good as if we stop the S process at the stopping time of the first hitting of the S process of 0. And in particular, we see that this random variable, which is the option here, is a random variable which can depend only on the behavior of the S process up to the first hitting of 0, which means that it's immeasurable with respect to the sigma field, which is generated or which belongs to that stopping time tau naught. So therefore, the phi tilde, likewise, is a phi tilde of the stopped process, which is a phi tilde which is measurable with respect to the sigma field ft naught. So therefore, it's the same as if I compute the conditional expectation of phi t naught tilde, of the conditional expectation of this phi tilde of S given the sigma field ft naught, just by measurability. There's these two random variables, or the conditional expectation is the identity operation. But if I insert my representation of the phi t, of the phi tilde through a full stochastic integral and a certain constant, I get inside the conditional expectation this sum, which of course I can decompose into the this expected value as a constant function of the constant, which is just the constant, and this constant is just this expected value, plus the conditional expectation of the martingale part, given the sigma field ft naught. But the process W tilde bar is W tilde is a martingale with respect to this filtration. The filtration that I'm working with here is, as a matter of fact, the filtration generated by the initial Brownian motion. So that's a martingale under Q, as we know. Then by optional stopping of this martingale, I get that this integration needs to be conducted only up to the infimum of t and t naught, which in other words means that this stochastic integral has to be computed only up to that stopping time maximally, and that therefore is part of that interval where I can effectively replace this dw term by the corresponding ds term, where this factor has to be included. But in the end, I have obtained a representation of my option as a certain constant plus a stochastic integral of a certain process, which I might call eta tilde of s, ds tilde s, where this integral is taken from 0 to t, and I have concluded that this option is attainable. This was the discussion for the case when the option is bounded, such that this square integrability condition is satisfied. And for general square integrable phi, I approximate phi by a sequence of cutoff versions of phi at the level minus n and n. Then this cutoff version of the phi function will be bounded, and we have, therefore, by the previous argument, an attaining portfolio or replicating portfolio strategy. And since phi is in L2, we have convergence of phi n towards phi in L2. And also by Ito isometry, we can easily convince ourselves that the corresponding sequence of portfolio strategies is a Cauchy sequence in this L2 space relative to the process S tilde, for instance, which means that there is an element eta, which will be then also a predictable process, in fact. And we can pass to the limit in this representation, which in particular means that also the contingent claim phi is attainable. Okay, so this concludes this proof of the very important statement that in the Black-Scholes model with two assets, every contingent claim is attainable provided it satisfies the square integrability condition. Okay, we can then wrap up this abstract discussion or very theoretical discussion of the Black-Scholes model by collecting a few more corollaries, which basically repeat what we have already found, but probably with slightly different flavor. Namely, if we find a stochastic process on this probability space, such that this stochastic process M tilde is a continuous martingale under this Q measure, which has the right terminal value coinciding with the discounted payoff of the contingent claim at terminal time, then the number Vt, which is defined as the martingale at time t, multiplied with e to the t, which is then by definition or by the property that it has the right terminal value just equally described as the expected value of the contingent claim under Q multiplied with this discounting prefactor. And this is the fair or rational price for this contingent claim if it is traded at an intermediate time t between the two extremal times 0 and time t. And why is that the case? Well, phi tilde, we know, is attainable. So there is a portfolio strategy such that the discounted value of the portfolio strategy at terminal time equals phi tilde. And for the discounted portfolio strategy, we can just write down in terms of an Ito expansion by Ito's formula. We can write this as the value of the portfolio at intermediate time t plus the stochastic integral from t to capital T of the corresponding portfolio strategy, where the integral is taken with respect to the discounted stock process. And at the same time, we know that this is the martingale at terminal time t. It's just an equality of certain random values. So therefore, if we take the conditional expectation of this equality given the sigma little f little t, we find that v tilde t, which is the value of the portfolio at time t, that by a martingale, if you like, that's the conditional expectation of the capital, that the portfolio, discounted portfolio at capital time t, conditioned on the sigma field ft. But this is the same as the portfolio value, as the martingale at terminal time given ft, which by martingale property is m tilde at t. So in other words, Vt, the actual value of that portfolio, is the non-discounted version of that, which is then e to the t times mt tilde. So this was just a big circle for showing a kind of trivial statement, namely that if we have a martingale, or if you have a process which is a martingale under Q and which realizes the right terminal value, then this martingale basically describes the value of the option at any intermediate time. Before we want to give an example of the effectiveness of this methods for pricing what we call exotic options, I want to add a few more remarks, which again basically repeat what we have found so far. Namely, if in the case of the previous theorem we have this martingale, this martingale under Q, which replicates the terminal value, and if we manage to write this martingale the infinity as a stochastic integral with respect to a certain stochastic integral of a certain process eta with respect to the S tilde process, then eta is in fact uniquely determined by this as the component in the stock investment of this uniquely determined replication portfolio. So that sometimes if you ask for a martingale representation of a certain option, you manage to do this replication and this replacement, then eta is right away the replication. So that is important in case when you do not only want to trade such portfolios, because for instance, if you find yourself in the position of an agent who sells such an option, then of course you expose yourself to the risks that come with this promise. Namely, you might end up having enormous obligation, which are described in this path functional phi. And what you would want to do is that you would want to set up, in fact, a replicating portfolio strategy, which you then put onto the computer or something like this, and which will then do the job for you to replicate your obligation, which will then mirror your obligation, but by means of just doing transactions on the financial market with the other two, initial assets that were there. So this replicating portfolio and having a concrete hands on how to set up a replicating portfolio will be very important for what is later called risk management. So you really want to make this trading happen in order to shield yourself from all the risks that come with the promise you sold to obey the teaching, to obey the claim phi. Okay, so whenever you have such a martingale which replicates, then you can use this martingale in order to identify the hedging strategy. And Q, this measure Q, which we were constructing, of course, plays here a very important role because it is the measure under which we look for martingale representations, and it is also the measure which we use in order to compute the actual price by just computing the conditional, the expectation of the payoff function under this measure. So it's a very central element in this theory, and it is called the equivalent martingale measure. It's called martingale measures because all prices of all assets under this martingale, under this measure, appear as martingales. Therefore, it's called a martingale measure, and it's equivalent because it has the same zero sets. And in fact, in the Black-Scholes world, the measure Q is uniquely determined by these two requirements. So it's therefore called the equivalent martingale measure, and we have this important pricing formula that we had now already a couple of times, that the price, the fair and rational price for both the buyer and the seller, on which both can agree, of that derivative is given as the mean discounted payoff of that contingent claim given under this martingale measure Q. And therefore, this whole method is also sometimes called the risk-neutral evaluation method. So once you have understood the method, and once you even have this martingale measure, which is defined by this martingale property of all discounted stocks, then computing the price of an option is then just an exercise in integration theory. So the method is absolutely general and will rely heavily on the existence of this martingale measure. And it's called also sometimes the risk-neutral measure, because under this measure Q, the price of an option is not only basically, it's just given as an expected value of this option, or the expected value of the discounted payoff of this option. Which means that the same two options give the same price if they have the same mean discounted payoff, regardless of any further information on these options. So one option might be, or one contingent claim might be, in fact, deterministic, will not depend on randomness at all, and the other option will be probably very varying and will have very big variance. But both options, both contingent claims, will have the same value if they have the same expectation. And any other information about the variance and the further risks which come with that or the other option are neglected under this measure Q, or under this method. And therefore, this measure is called the risk-neutral measure, because it's that measure that you use in order to compute a fair bet, a fair price of a bet, where you do not care what actual risks are involved with the bet, where in financial mathematics language, risk is more or less the equivalent of variance, of non-deterministic behavior. So that's why the whole method is called the risk-neutral pricing method. Okay. I want to show the effectiveness of what we have just learned and this abstract approach in the case of a first example of what one could call an exotic option, which is an option which is really path dependent. And one simple example of such an exotic option, which is still very easy to treat, would be something like this up and out call, which would be again a European call in the same shape, as the same form as we had when we were discussing at the very beginning of the Black-Scholes formula, the European call. But this money is paid off, or is paid under the option phi, only if the stock value in all intermediate times has not exceeded a certain threshold number B. So this means that we get this amount of money at terminal time only if the stock in intermediate time was not above that number. Obviously, this is really an honestly path-dependent option, because it takes into account not only the value of the trajectory at terminal time, but also the full behavior of that trajectory in all intermediate times. And in order to come up with a pricing and hedging strategy for that, we will make use of the following analytic proposition, which is something that we have already seen effectively in the context of the plain European call. Namely, our goal now is to recall that our goal now basically is just, if you like, to construct a martingale by the previous theorems. All we have to do is to construct a martingale or a stochastic process that we can write as a stochastic integral with respect to the S tilde process, which has the right payoff at terminal time. And to do this, we will solve a certain PDE similar to what we did for the Black-Scholes formula for the plain European call. But since we have lots of situations when the payout is effectively zero, this PDE needs to be solved only for times which lie in the time parameter interval 0t, and stock values which lie between 0 and b, where b is this threshold which appears. Okay, and what do we want to do? Well, we solve as we did before in the case of the European stock, if you like, and basically this will always be a strategy when we deal with Black-Scholes model to resolve the Black-Scholes partial differential equation, but now only inside this domain, which is the effective domain in space-time, in which anything of interest can happen to the stock. But now we have to pay attention to the boundary value of this Black-Scholes PDE, or the boundary condition that we impose on this domain. Namely, we impose the following boundary condition: if whenever we are at the x equals 0 part or boundary of that two-dimensional domain, we require that the solution be 0. Because this means that the stock is 0, and therefore the stock would not recover from that value, because it's a non-negative martingale under Q, and so therefore we won't have any payoff afterwards. We also require this value function to be 0 whenever we are on the right boundary, so whenever we are on x equals b of the boundary, because this corresponds to the case that the stock is hitting the level b, which leads to a 0 value of the payoff. And then at terminal time, capital T, we require that the function as a function of x is exactly the payoff of that of the given stock, which of the given option, which is the payoff we receive if the trajectory has never touched this one of the two boundaries. And then we have the following lemma, that if we plug in the discounting factor in front as a factor of this function v, and then we evaluate the function at the time t and at position of the stock, at least up to the moment of the first hitting, then the first hitting of the boundary b, then this process, this psi process, is a Q martingale under this measure Q, whose terminal value at capital T coincides with the payoff of the discounted option. So that's a little lemma. And in particular, as a consequence of what of our general methodology, we can say that the fair price on which both investor, a buyer and seller of the option, will agree upon will be, at time 0, for instance, will be the evaluation of this v function for time parameter 0, evaluated at the position of the stock value that we have at the beginning of our time interval. And moreover, the strategy in order to replicate that option by means of a portfolio strategy is given by the the space derivative of this function evaluated at time t, and where you insert the current stock position as a second spatial argument. Okay. And, this will now be very easy to prove. We have just to check that this process Q is a Q martingale, and in order to do that, of course, we just apply the Ito formula. So we do the Ito formula for this combination of processes, which is just the time evolution of this discounted V function. And then we compute and insert the chain rule, use the relation among the coefficients and all this, and we finally see that this is that will be the end of this computation, and it's something that you can do alone. That after you write out all the terms, there's lots of cancellations, and the only thing that remains is a stochastic integral with respect to this W tilde process, where in front you have e to the minus RT sigma S V of x and so forth, the dW, which first means that this process is in fact a Q martingale, at least in particular, and when you stop the whole thing upon the first entry of S on these two boundaries. And secondly, by the very construction of the boundary values for this V function, we also convince ourselves that at terminal time, this psi process satisfies the right payoff. This then tells us that, in fact, the process psi at initial time is the fair value of this martingale, of this option. And finally, this particular representation of the increment tells us exactly that the investment strategy eta is given by this term, because it's just this division by sigma and s, which gives us then which isolates the factor eta in front of the ds integral. This concludes this example, and you see that the abstract understanding of this Black-Scholes evaluation mechanism was very helpful for an efficient computation or an efficient treatment of this already kind of difficult and exotic option, which you could also understand, of course, as a complicated bet on, it's basically just a complicated bet on the financial market. Okay, and just as an outlook, the real world out there is unfortunately much more complicated than just the Black-Scholes formula, because you have more than just two assets in which you can invest, and the options that you can treat are typically much more dependent on many more parameters. And when you deal with more the higher dimensional financial market models, then they tend to be incomplete, which means that they have typically more than just one equivalent martingale measures. So you have an abundance of martingale measures Q, and all these different martingale measures Q provide certain pricing formulas, and then you have to make some choice, which is another level of an optimization problem, which needs to be addressed at that point. So the real world is unfortunately more complicated than the Black-Scholes world, but the Black-Scholes formula and the Black-Scholes approach is still benchmark approach for basically all other financial market models, and you have understood quite a bit of the approach if you are familiar with what we have just discussed about this in this very simple Black-Scholes world. Okay, so that's the end of our excursion into financial mathematics in the course of this lecture, and in the remaining one or two lectures we will finally touch the subject of stochastic differential equations with more general coefficients than just constant coefficients or something, and that will then ultimately conclude our journey in this semester through the theory of stochastic processes.